North Korea continues to field missiles, armored vehicles, and air defense systems despite lacking the parts, suppliers, and industrial depth normally required to sustain modern weapons production. This is not the result of efficiency or self-sufficiency, but adaptation under permanent constraint. Cut off from global supply chains by sanctions and isolation, its military industry operates in reverse, designing weapons around what can be obtained, substituted, or salvaged rather than what is ideal. Factories function without reliable inputs, relying on reverse engineering, cannibalization, and improvised manufacturing to keep production moving. The result is an arsenal built on compromise, systems that work well enough to deploy and deter, but uneven in quality, difficult to sustain, and defined as much by scarcity as by intent. Factories without supply chains. North Korea's ability to keep producing military hardware despite chronic shortages rests on an industrial paradox: factories that operate without functional supply chains. In most modern defense industries, production depends on tightly coordinated networks of suppliers, standardized components, and predictable logistics. In North Korea, those networks are fragmented or absent. Yet weapons continue to roll out of assembly halls, not because supply chains function, but because the system has adapted to their collapse. The breakdown began with isolation. Sanctions, export controls, and financial restrictions progressively severed access to foreign components, raw materials, and specialized machinery. Precision bearings, electronics, alloys, and machine tools became difficult or impossible to import legally. For civilian industries, this kind of disruption would halt production. For military factories, it forced a different response: build with whatever is available. Without reliable suppliers, factories reverse the normal order of manufacturing. Instead of designing weapons around standardized parts, engineers design around shortages. If a specific component cannot be sourced, the design changes. Dimensions are altered, tolerances widened, and performance requirements adjusted to match what local workshops can produce. This approach sacrifices efficiency and consistency, but it allows production to continue. The absence of supply chains also eliminates specialization. In conventional systems, factories focus on assembly, while suppliers handle components. In North Korea, factories are expected to do everything. They cast metal, machine parts, wind motors, fabricate electronics, and assemble final systems under one roof or within tightly controlled local clusters. This vertical integration reduces dependence on external inputs, but increases internal strain and inefficiency. Quality control suffers as a result. Without standardized inputs, variation becomes unavoidable. Two components nominally serving the same function may differ significantly in material quality or dimensions. Workers compensate through manual fitting, shimming, and adjustment. Weapons are built individually rather than uniformly, undermining interchangeability and complicating maintenance once deployed. Factories also depend heavily on cannibalization. Older equipment, obsolete weapons, and damaged systems become parts donors. Components are stripped, refurbished, and reused in new builds. This practice fills gaps left by missing supply chains but introduces hidden weaknesses. Parts carry unknown wear histories, fatigue, and defects that are difficult to detect without advanced testing equipment. The lack of supply chains reshapes labor practices as well. Skilled technicians become more valuable than automated processes. Workers are trained to improvise, repair, and adapt rather than follow fixed procedures. This human flexibility replaces industrial consistency. Production relies less on precision machinery and more on experience, judgment, and manual correction. Energy shortages further complicate factory operations. Intermittent electricity disrupts machine tools, heat treatment, and assembly lines. Factories compensate by batching work around power availability, using backup generators, or reverting to less energy-intensive processes. Output becomes uneven, but continuity is preserved. Secrecy masks many of these problems. Unlike commercial manufacturers, North Korean military factories are not accountable to markets or customers. Failures are hidden. Defects may not be discovered until weapons are deployed or tested. Feedback loops are slow and opaque, allowing production to continue even when underlying issues persist. This system generates internal conflict. Designers push for performance improvements that require better components. Factory managers prioritize producibility with existing resources. Military end users demand reliability. These pressures collide within a constrained environment, where no party can fully achieve its goals. Compromise becomes the default operating mode. Factories without supply chains also struggle with scalability. Producing small batches is possible through improvisation. Scaling up output magnifies shortages, exhausts cannibalization sources, and overwhelms internal capabilities. As a result, production surges are difficult to sustain, and output often fluctuates. The strategic implication is mixed. On one hand, North Korea demonstrates resilience. It can produce weapons under conditions that would cripple other systems. On the other hand, the absence of supply chains imposes a ceiling on quality, reliability, and consistency. Weapons may exist in quantity, but their performance is uneven and difficult to predict. Factories without supply chains are not efficient or modern. They are adaptive, brittle systems designed to survive constraint rather than excel. They function by absorbing inefficiency, variability, and risk internally, pushing problems downstream to testing, deployment, and maintenance. In the end, North Korea's military factories operate not as nodes in a global industrial network, but as self-contained improvisational systems. They keep building war machines without parts by redefining what having parts means. Production continues, but at the cost of reliability, transparency, and control. The factories run, but they do so on the edge of what an industrial system can sustain without collapsing entirely. Reverse engineering under sanctions. Under sustained international sanctions, North Korea has turned reverse engineering from a supplementary practice into a core survival strategy for its military-industrial complex. Cut off from formal supply chains, licensed production, and legal technology transfer, the state relies heavily on dissecting foreign systems, legacy equipment, and captured or imported hardware to reproduce capabilities it can no longer acquire directly. This process keeps weapons programs alive, but it introduces technical, economic, and strategic problems that shape everything built under constraint. Reverse engineering begins with scarcity. Modern weapons depend on components, microelectronics, precision bearings, guidance sensors, specialized alloys that North Korea cannot reliably import. When a complete system or component enters the country through limited trade, smuggling, or diplomatic channels, it becomes a template rather than a consumable. Engineers disassemble it, document dimensions, materials, and functions, and attempt to replicate its behavior using domestic tools and substitutes. The challenge is that reverse engineering reveals what something does, not how it was economically or reliably produced. Foreign systems are designed around industrial ecosystems that do not exist locally. When North Korean engineers recreate a part, they often lack the original materials, tolerances, or manufacturing methods. As a result, replicated components are functionally similar but structurally different, introducing performance gaps and durability issues. Electronics present the greatest obstacle. Modern military systems rely on integrated circuits, microcontrollers, and sensors produced through advanced semiconductor processes. North Korea cannot replicate these processes at scale. Instead, engineers substitute older generation chips, discrete components, or simplified circuits that approximate the original function. This allows systems to operate, but at reduced precision, speed, and resistance to interference. Mechanical systems are easier to reverse engineer but still problematic. Engines, gearboxes, and artillery components can be measured and copied, but material quality is inconsistent. Alloy composition may be approximated, heat treatment uneven, and machining precision variable. Engineers compensate by overbuilding parts, increasing weight and reducing efficiency to preserve strength. Reverse engineering also depends heavily on trial and error. Without access to original testing data or design rationale, engineers must discover limits experimentally. This extends development timelines and increases failure rates. Components may perform adequately in isolation but fail when integrated into larger systems. Each iteration consumes time, materials, and scarce test opportunities. Sanctions intensify these challenges by restricting feedback. International isolation limits exposure to evolving technologies and design standards. Reverse engineering often targets systems that are already outdated by global standards, locking domestic production into older technological baselines. While this still represents progress internally, it widens the gap with more advanced adversaries. There are also internal conflicts. Military planners demand performance parity with foreign systems. Engineers understand the limitations of domestic replication. Factory managers prioritize producibility over fidelity. These competing pressures result in compromises that satisfy immediate needs but undermine long-term reliability. Weapons may meet appearance or basic function requirements while falling short under sustained use. Reverse engineering under sanctions also creates dependency on single examples. When only 1 or 2 units of a foreign system are available, any design flaw or damage in the sample propagates through all copies. Without multiple reference points, errors are difficult to detect. Production can unknowingly replicate defects, embedding them across an entire weapon batch. Secrecy compounds the problem. Failures revealed during testing or deployment are often classified, limiting institutional learning. Engineers may not receive full feedback from field units, slowing improvement cycles. The system favors output over refinement, encouraging continued production even when flaws are known internally. Despite these weaknesses, reverse engineering offers strategic advantages. It reduces dependence on imports, bypasses licensing restrictions, and allows rapid imitation of perceived threats. Even imperfect copies can alter regional security calculations by forcing adversaries to assume capability rather than certainty of failure. However, this approach has limits. Reverse engineering cannot easily reproduce advanced materials science, microfabrication, or software ecosystems. As global military technology becomes more integrated and software-driven, the gap between imitation and original design grows harder to bridge. Reverse engineering under sanctions is therefore both a strength and a trap. It enables continued weapons production in the absence of supply chains, but it locks the system into reactive development. Innovation becomes incremental, constrained by what can be copied rather than what can be conceived freely. In the end, North Korea's reliance on reverse engineering reflects adaptation under pressure, not technological independence. Weapons are built, tests are conducted, and production lines run. Yet every system carries the imprint of scarcity, functional, often intimidating, but shaped by compromise at every level. Reverse engineering keeps war machines alive under sanctions, but it also ensures that each new build inherits the limitations of the constraints that created it. When shortages become design constraints. In North Korea's military-industrial system, shortages are not temporary disruptions to be solved later. They are permanent conditions that shape how weapons are designed from the outset. Unlike conventional defense industries, where engineers design systems first and procurement fills in the parts, North Korean designers work in reverse. What can be obtained or fabricated defines what can be built. Scarcity is not an obstacle to design. It is the design constraint. This inversion fundamentally alters engineering priorities. Performance targets are adjusted downward to match material availability. If high-grade alloys cannot be sourced consistently, components are thickened rather than strengthened. If precision electronics are unavailable, systems are simplified to rely on mechanical or analog solutions. Designs emphasize tolerance for variation rather than optimization, accepting inefficiency as the price of producibility. Material shortages are the most visible constraint. Modern weapons rely on specialized steels, composites, and heat-treated alloys that require stable inputs and precise processing. North Korean factories often lack both. As a result, designers compensate by over-engineering parts. Barrels are heavier, frames are bulkier, moving components are slower but sturdier. Weight increases, but reliability under uncertain material quality improves. Electronics shortages impose even harsher limits. Guidance systems, sensors, and fire control electronics are difficult to source and harder to reproduce domestically. designers respond by reducing reliance on digital integration. Weapons are built to function with minimal electronics or with modular add-ons that can be omitted if components are unavailable. This creates systems that are less precise but more survivable under supply disruption. Standardization also suffers. In systems with reliable supply chains, parts are interchangeable. In North Korea, designers expect variation. Components are designed with adjustable mounts, oversized tolerances, and manual calibration points. Assembly becomes an act of fitting rather than snapping parts together. Maintenance crews must adapt each weapon individually, increasing labor demands and reducing field efficiency. Shortages also constrain testing and refinement. Limited access to materials means fewer prototypes can be built. Fewer prototypes mean less data. Engineers are forced to accept higher uncertainty, pushing systems into production with incomplete validation. Field testing substitutes for controlled experimentation, shifting risk from development to deployment. These constraints create internal conflict. Military planners demand systems that match or deter foreign capabilities. Engineers understand that such parity is unrealistic given available inputs. Factory managers prioritize designs that can be produced reliably with existing tools. The resulting compromises often satisfy political requirements while embedding technical weaknesses that only appear later. Cannibalization further shapes design philosophy. Knowing that future production may depend on salvaged parts, designers create systems that can accept components from older models. Backward compatibility becomes a necessity, not a convenience. This keeps production lines moving but locks new designs into outdated architectures, limiting advancement. Energy shortages reinforce these patterns. Unreliable electricity constrains machining, heat treatment, and electronics fabrication. Designers favor processes that can tolerate interruptions or be completed manually. Precision is sacrificed for robustness. Designs evolve to fit the rhythm of power availability rather than ideal manufacturing sequences. Over time, these constraints become normalized. Engineers are trained to think in terms of scarcity. Innovation focuses on workaround rather than breakthrough. Creativity is applied to adaptation, not optimization. This produces a distinctive engineering culture, one that values resilience under deprivation but struggles to escape it. Strategically, this approach yields mixed outcomes. On one hand, it enables continued production under conditions that would paralyze other systems. Weapons exist in quantity, and some perform adequately for their intended roles. On the other hand, the gap between design intent and operational reality widens. Reliability varies. Maintenance burdens increase. Performance is inconsistent across units. The deeper problem is path dependence. Once shortages shape design, escaping them becomes difficult. New systems inherit old compromises. Improvements are incremental and constrained by legacy limitations. Even if access to better materials or components improves temporarily, production systems may be unable to exploit them fully. When shortages become design constraints is not merely a description of North Korean engineering. It is a warning about what happens when scarcity becomes permanent. Design ceases to aim for excellence and instead aims for survival. Systems work, but they do so by absorbing inefficiency and risk internally. In the end, North Korea's war machines are not designed in spite of shortages but because of them. Every bolt, circuit, and assembly reflects an absence as much as a presence. Production continues, weapons roll out, and tests are conducted. But the limits imposed by scarcity are baked into the design itself. Shortages do not delay progress, they define its boundaries, cannibalizing old weapons to build new ones. In North Korea's military-industrial system, old weapons are not retired. They are recycled. Cannibalization, the systematic dismantling of existing equipment to supply parts for new builds, has become a central production method rather than an emergency measure. This practice allows factories to continue output despite shortages, but it introduces deep technical, logistical, and strategic problems that shape the quality and reliability of the weapons produced. Cannibalization begins with necessity. Sanctions, limited imports, and fragile domestic manufacturing capacity make consistent production of key components difficult. Engines, guidance elements, optics, electronics, and precision-machined parts are especially hard to replace. Older weapons, damaged equipment, and obsolete platforms become the most reliable source of these items. Instead of being scrapped, they are harvested. This process reverses the normal life cycle of military hardware. In most systems, new weapons replace old ones. In North Korea, old weapons enable new ones. Factories maintain inventories of legacy equipment, specifically to serve as parts donors. Vehicles, artillery pieces, and missiles may be dismantled not because they failed, but because their components are more valuable elsewhere. Cannibalization provides immediate benefits. It bypasses the need to manufacture complex components from scratch. Parts that once met foreign or higher domestic standards can be reused directly or refurbished. This allows new weapons to incorporate elements that local factories struggle to replicate, improving baseline capability in the short term. However, the hidden costs are severe. Cannibalized parts carry unknown histories. Components may have endured stress, corrosion, fatigue, or improper storage. Without advanced diagnostic tools, factories cannot fully assess remaining service life. Visual inspection and basic testing substitute for comprehensive evaluation, increasing the risk of latent failure. Standardization collapses under this model. Two weapons of the same type may contain different internal components sourced from different donor systems. Maintenance becomes individualized. Field units cannot rely on interchangeable parts. Repairs require improvisation, further cannibalization, or return to factory-level support, slowing operational readiness. Design compromise becomes inevitable. Engineers must ensure that new systems can accept salvaged components of varying dimensions and performance. Mounts are adjustable. Interfaces are widened. Software and controls are simplified to accommodate inconsistency. These design choices preserve producibility but reduce precision, efficiency, and integration. Cannibalization also creates a shrinking pool of donors. Each new weapon built from old parts reduces the number of legacy systems available for future harvesting. Over time, the system consumes its own past. As older platforms are exhausted, factories must rely increasingly on deeper refurbishment, lower quality substitutes, or incomplete assemblies. This dynamic produces internal conflict. Military planners want new systems in quantity. Factory managers worry about running out of donor equipment. Engineers push for designs that stretch salvaged components further. The result is a tension between immediate output and long-term sustainability, with short-term demands usually prevailing. Quality control suffers accordingly. Failures discovered during testing or deployment are difficult to trace. When a weapon malfunctions, the cause may lie in an individual cannibalized component rather than the overall design. This complicates corrective action and allows systemic issues to persist unnoticed. Secrecy masks these weaknesses. Production numbers and test results are tightly controlled, limiting feedback loops. Weapons may enter service despite known variability. Reliability becomes probabilistic rather than assured, forcing operators to compensate through redundancy and caution. Cannibalization also shapes doctrine. Knowing that replacement parts are scarce, designs favor ruggedness over sophistication. Systems are expected to tolerate failure and be repaired locally. This aligns with shortages but constrains performance growth and integration with more advanced capabilities. Strategically, cannibalization offers resilience under pressure. It allows continued production despite isolation and disruption. Adversaries must assume that North Korea can field new systems even when supply chains are cut. That uncertainty has deterrent value. Yet cannibalization is not a substitute for manufacturing depth. It delays the consequences of scarcity but does not eliminate them. Each generation of weapons inherits the wear and compromises of the last. Innovation becomes constrained by what exists to be dismantled rather than what can be newly created. Over time, this approach increases brittleness. A system built from recycled components can function, but its reliability is uneven and difficult to predict. Large-scale conflict or sustained high-intensity use would rapidly expose these weaknesses, exhausting the stock of salvageable parts. Cannibalizing old weapons to build new ones is therefore both adaptive and self-limiting. It reflects ingenuity under constraint, but also a cycle that feeds on itself. The factories keep running, weapons keep appearing, and production statistics can be maintained. But beneath that continuity lies erosion. In the end, cannibalization sustains output by consuming history. It keeps war machines coming off assembly lines without secure access to parts, but it does so by trading long-term reliability for short-term survival. The system works, but only by dismantling what it once built, turning yesterday's weapons into today's components and tomorrow's problem. Quality failures, hidden by secrecy. In North Korea's military-industrial system, quality failures are not eliminated. They are concealed. Secrecy functions as both a shield and a liability, allowing weapons production to continue despite serious defects while preventing the corrective feedback necessary to improve reliability. What emerges is an arsenal that appears functional on paper and in controlled displays, but whose true performance is uneven, unpredictable, and often unknown even to its own builders. Secrecy begins at the factory level. Production data, defect rates, and failure reports are classified. Unlike commercial or competitive defense industries, there is no external auditing, no customer rejection process, and no transparent accountability. When a component fails inspection or a weapon underperforms, the issue is handled internally, if it is addressed at all. The incentive is not to document problems, but to avoid reporting them upward. This distorts quality control. Inspectors operate under political pressure to meet quotas and deadlines. Rejecting too many parts can be interpreted as obstruction or incompetence. As a result, standards are flexible, and marginal components are often accepted. Quality becomes relative rather than absolute, defined by what can be produced rather than what should be produced. Testing is similarly constrained. Live fire trials and system evaluations are expensive, visible, and risky. Failures during testing carry reputational and political consequences. This encourages selective testing under favorable conditions rather than exhaustive validation. Systems that pass limited trials may enter production without having been stressed across their full operating envelope. Secrecy also disrupts feedback loops from the field. When deployed weapons malfunction, reporting those failures can reflect poorly on units, commanders, or factories. Field reports are filtered, delayed, or softened before reaching engineers. By the time information returns to production facilities, it is incomplete or distorted, limiting meaningful corrective action. The result is defect persistence. Problems are treated as isolated incidents rather than systemic flaws. A failed missile test may be attributed to operator error. A vehicle breakdown may be blamed on maintenance practices. Without transparent data aggregation, patterns remain hidden. Factories continue producing systems with known weaknesses because those weaknesses are never formally acknowledged. Cannibalization and improvised components exacerbate this problem. When weapons are built from reused or substituted parts, variability increases. Secrecy prevents tracking which units received which components. Failures cannot be traced back to specific batches or donors. Quality control loses its ability to isolate causes, turning troubleshooting into guesswork. Secrecy also protects unrealistic performance claims. Official statements and propaganda emphasize capability, range, and power, while omitting reliability and sustainability. Engineers and operators are expected to align with these narratives. Admitting that a system works only intermittently or under narrow conditions contradicts official messaging and is therefore discouraged. This creates internal conflict. Engineers know the limitations of what they are producing. Factory managers know where corners were cut. Military planners assume higher reliability than actually exists. Secrecy prevents these groups from openly reconciling expectations with reality. Decisions are made based on assumed performance rather than measured performance. Over time, secrecy shifts the burden of quality from production to operation. Units are expected to compensate for unreliable equipment through redundancy, improvisation, and caution. Multiple systems are deployed to ensure at least one functions. Operators learn to work around defects rather than expect fixes. This masks quality failures in peacetime, but magnifies them under stress. Strategically, this opacity cuts both ways. Adversaries cannot easily assess the true reliability of North Korean weapons, creating uncertainty. At the same time, North Korea itself lacks a clear picture of its own capabilities. Planning is based on optimistic assumptions, increasing the risk of miscalculation. Secrecy also prevents institutional learning. In systems where failures are openly analyzed, each defect improves future designs. In North Korea's system, failures are buried, lessons are lost. New weapons inherit old flaws because acknowledging those flaws carries risk. Innovation becomes conservative, focused on appearance and basic function rather than robustness. The longer secrecy hides quality failures, the harder they are to correct. Designs ossify. Production methods stabilize around flawed assumptions. When failures finally surface publicly during tests or demonstrations, they appear sudden, but they are the product of long-suppressed problems. Quality failures hidden by secrecy do not mean weapons never work. Many function well enough to test, deploy, and threaten, but their reliability is uneven, and their true limits are obscured. Secrecy sustains production by suppressing bad news, but it undermines confidence and control within the system itself. In the end, secrecy allows North Korea to keep building war machines without confronting their shortcomings. It replaces transparency with narrative, data with assertion, and quality assurance with compliance. Weapons emerge, factories run, and numbers can be reported. Yet beneath that surface lies a system where defects persist, not because they cannot be fixed, but because admitting them is more dangerous than living with them. Smuggling, substitution, and improvised components. North Korea's ability to continue building modern weapons without reliable access to parts depends on a three-part survival strategy: smuggling what cannot be made, substituting what cannot be obtained, and improvising when neither option works. This system does not replace a functioning supply chain. It compensates for its absence. The result is an arsenal assembled through workaround rather than standardization, where capability exists, but consistency does not. Smuggling fills the most critical gaps. Certain components, precision bearings, advanced electronics, machine tools, and specialty materials are difficult or impossible to manufacture domestically at acceptable quality. These items enter the country through covert trade networks that exploit weak enforcement, falsified documentation, and intermediaries across multiple jurisdictions. Components are often mislabeled as civilian goods, industrial spares, or scrap to evade detection. However, smuggling is unreliable by nature. Quantities are small, deliveries unpredictable, and quality inconsistent. Factories cannot plan production around smuggled components with confidence. Instead of forming a stable supply, smuggling creates sporadic opportunities. When parts arrive, they are treated as strategic assets, allocated to priority programs rather than integrated into routine manufacturing. Substitution becomes the default response to this uncertainty. When a specific component cannot be sourced, engineers replace it with something that performs a similar function, even if performance is degraded. Commercial-grade electronics replace military-grade parts. Civilian motors stand in for hardened actuators. Analog systems replace digital ones. Designs are altered mid-production to accommodate what is available rather than what was intended. These substitutions ripple through entire systems. A weaker component requires reduced operating loads, thicker housings, or simplified control logic. Performance specifications are quietly adjusted downward. Weapons still function, but their operating envelopes narrow. Precision declines. Durability becomes unpredictable. Substitution preserves output, but it undermines uniformity. Improvisation bridges the remaining gaps. When neither smuggling nor substitution provides a solution, factories fabricate components using basic tools and manual processes. Circuit boards are assembled from discrete parts. Optical elements are reused, polished, or repurposed from civilian devices. Mechanical components are machined with wide tolerances and fitted by hand. Skilled labor compensates for missing automation. This improvisation relies heavily on human expertise. Technicians develop localized solutions that work for a specific batch or even a single unit. These fixes are rarely documented systematically. Knowledge remains tacit, passed informally rather than institutionalized. When personnel change or facilities shift, that expertise can disappear, forcing reinvention. The combination of smuggling, substitution, and improvisation destroys standardization. Two weapons of the same model may share little internally. Maintenance becomes individualized. Spare parts compatibility is limited. Field units must adapt continuously, relying on cannibalization or further improvisation to keep systems operational. This creates internal tension. Engineers design systems with ideal components in mind, knowing those components may never arrive. Factory managers push for producibility with existing materials. Military planners expect performance based on official specifications rather than practical limitations. These conflicting expectations collide during testing and deployment, where failures expose the gap between design intent and material reality. Secrecy masks much of this instability. Official descriptions emphasize capability, not reliability. Variability is hidden rather than addressed. Failures are attributed to handling or training rather than component inconsistency. This allows production to continue, but it prevents systemic correction. Strategically, this approach offers resilience. North Korea can bypass sanctions, adapt to shortages, and field weapons under conditions that would halt conventional programs. Even imperfect systems force adversaries to plan for worst-case scenarios. Uncertainty itself becomes a form of deterrence, yet the costs are cumulative. Improvised components age poorly, substituted parts fail earlier, smuggled electronics lack long-term support. As systems grow more complex, improvisation becomes harder to sustain. Software-driven integration, advanced sensors, and precision guidance magnify the consequences of inconsistency. There is also a scalability limit. Smuggling cannot support mass production. Improvisation cannot easily be automated. Substitution stretches designs only so far. Production surges exhaust available workarounds, leading to bottlenecks and declining quality. The system can produce weapons, but it struggles to produce them reliably at scale. Smuggling, substitution, and improvised components are therefore not signs of strength alone. They are indicators of constraint. They reveal a system operating in permanent contingency mode, where survival replaces optimization and continuity replaces excellence. In the end, North Korea's war machines are not built from complete parts lists or stable suppliers. They are assembled from opportunities, compromises, and human ingenuity under pressure. Weapons emerge, tests are conducted, and production lines keep moving. But beneath that output lies an industrial reality held together not by precision manufacturing, but by adaptation to absence. Testing weapons built from mismatched parts. Testing is the point at which North Korea's improvised weapons programs confront reality. When systems are assembled from mismatched parts, smuggled components, substituted materials, and cannibalized hardware, testing shifts away from formal validation and toward risk management. The objective is not to confirm that a weapon meets ideal specifications, but to determine whether it functions well enough to justify deployment under severe material, industrial, and political constraints. The core challenge is inconsistency. Weapons built from non-standardized parts do not behave predictably. Two systems assembled from the same design may respond differently under identical conditions. Engineers cannot assume that test results will generalize across production batches. Each test reflects the behavior of a specific configuration rather than a representative model, undermining confidence in repeatability and long-term reliability. This reality forces a fundamental change in testing philosophy. Instead of exhaustive validation across environments and stress levels, tests are limited, selective, and outcome-driven. Successful results are emphasized, while marginal or ambiguous data are often sidelined. A system that works once under controlled conditions may be accepted, even if its performance under sustained use remains uncertain. Testing becomes a gatekeeping exercise rather than a learning process, focused on approval rather than refinement. Mismatched components also complicate instrumentation and diagnostics. Sensors and monitoring equipment may not be integrated consistently across units, or may themselves be improvised. Some tests rely heavily on external observation rather than embedded telemetry. Failures are often detected only after visible malfunction instead of through early warning indicators, reducing the ability to isolate root causes or anticipate cascading faults. Reverse-engineered components add another layer of uncertainty. When parts are copied from foreign systems without full understanding of materials, tolerances, or manufacturing processes, engineers lack reliable baselines. A failure could stem from flawed replication, material fatigue, poor substitution, or incompatibility elsewhere in the system. Distinguishing between these causes is difficult without advanced testing infrastructure, which remains limited. Testing timelines are further constrained by scarcity. Each test consumes fuel, rare components, and political capital. Failed tests carry reputational risk domestically and internationally. As a result, pressure exists to minimize test frequency and maximize the appearance of success. This bias favors demonstrations over diagnostic experimentation, reducing opportunities to uncover latent defects before deployment. Environmental testing presents a particularly acute challenge. Weapons assembled from mixed-quality components may perform acceptably under ideal conditions, but fail under extremes. Cold, heat, vibration, shock, and prolonged operation expose weaknesses in seals, electronics, and structural interfaces. Conducting repeated environmental tests requires facilities, time, and replacement parts that are scarce. Engineers often extrapolate from limited data, accepting higher uncertainty as unavoidable. Missile and rocket testing illustrates these constraints clearly. Guidance systems assembled from substituted electronics may function during short flights, but drift over longer durations. Engines built from mixed alloys may meet thrust requirements, yet exhibit inconsistent burn characteristics. A single successful launch does not guarantee consistency, but it may be treated as sufficient proof of viability under political pressure. Ground systems face similar problems. Armored vehicles, artillery, and air defense platforms built from mismatched parts often require manual calibration before testing. Adjustments are made on a unit-by-unit basis. Once a configuration passes, it may be frozen even if suboptimal, because reproducing that exact setup later may be impossible due to part variability. Testing also exposes institutional tension. Engineers seek additional data and refinement. Military leadership prioritizes deployment timelines and deterrence signaling. Factory managers push to accelerate production before parts availability changes. These competing pressures compress testing phases and increase reliance on judgment and political necessity rather than empirical certainty. Despite these limitations, testing still plays a critical role. It filters out the most dangerous failures and identifies configurations that function acceptably. Even imperfect testing improves survivability compared to no testing at all. Systems that consistently fail are modified or abandoned, while those that perform adequately are scaled cautiously. Testing weapons built from mismatched parts is therefore an exercise in compromise. It balances scarcity against necessity, secrecy against learning, and demonstration against diagnosis. Defects are not eliminated. They are managed within acceptable political and strategic limits. The result is an arsenal validated not through industrial rigor, but through functional sufficiency, uneven, unpredictable, and constrained by the parts from which it is built. An arsenal held together by necessity. North Korea's modern arsenal is not the product of a coherent industrial ecosystem, but of sustained improvisation under pressure. Sanctions, isolation, and chronic material shortages have forced weapons programs to evolve around constraint rather than optimization. As a result, the country's military hardware is less a standardized force than a collection of systems held together by necessity, engineered to function acceptably. not perfectly, and to endure just long enough to serve strategic and political goals. At the foundation of this reality lies scarcity, access to advanced materials. Precision manufacturing equipment and reliable supply chains is uneven and unpredictable. Components are acquired through smuggling networks, reverse engineering, or domestic substitutes that only approximate original specifications. What cannot be sourced is improvised. What cannot be replicated is adapted. This produces weapon systems assembled from mismatched parts, each reflecting the conditions under which it was built rather than a uniform design standard. The consequences of this approach are structural. Variability becomes endemic. Two units of the same system may share outward appearance, yet differ internally in materials, electronics, or tolerances. Engineers cannot rely on statistical consistency across production runs. Instead, each weapon becomes a discrete solution to a localized problem, built with whatever components were available at the time. Reliability is therefore uneven, and predictability becomes a luxury rather than an assumption. Design compromises accumulate quickly. Systems are often overbuilt in some areas and under-engineered in others, reflecting uneven access to quality components. Redundancy substitutes for precision. Manual adjustments compensate for poor integration. Maintenance requirements increase as parts wear unpredictably or fail outside expected cycles. Field units adapt through procedural workarounds, accepting higher logistical burden in exchange for continued operability. This necessity-driven approach also reshapes doctrine. Weapons are not expected to perform flawlessly over extended campaigns. Instead, they are designed to function long enough to deter, to signal capability, or to deliver a limited but credible threat. Operational planning accounts for higher failure rates by emphasizing quantity, dispersal, and uncertainty. The arsenal's strength lies less in technical excellence than in its ability to complicate adversary calculations. Missile forces illustrate this dynamic clearly. Guidance systems assembled from substituted or reverse-engineered electronics may perform adequately over short durations but degrade under extended flight or environmental stress. Propulsion systems built from mixed alloys may achieve required thrust, yet exhibit inconsistent burn profiles. Each successful test demonstrates possibility, not consistency. Yet, under conditions of necessity, possibility is sufficient to justify deployment. Ground forces face parallel challenges. Armored vehicles and artillery platforms often rely on aging designs updated incrementally with whatever improvements are feasible. Fire control systems may be partially modernized while mechanical components remain outdated. Air defense systems integrate new sensors with legacy launchers, creating hybrid platforms that function through careful calibration rather than seamless integration. These systems demand skilled operators and frequent adjustment, trading ease of use for continued relevance. Institutional pressures reinforce this pattern. Engineers understand the risks inherent in mismatched systems, but time, resources, and political directives limit corrective action. Military leadership prioritizes visible capability and readiness. Production facilities must move forward before supply conditions change again. The result is an arsenal shaped by urgency, where refinement yields to deployment and adequacy replaces optimization. Secrecy compounds the problem. Failures are closely held, lessons compartmentalized, and feedback loops restricted. Without transparent institutional learning, systemic weaknesses persist across generations of equipment. Improvements occur, but unevenly, and often without resolving underlying inconsistencies. Each new system inherits not only design features but also the constraints and compromises of its predecessors. Yet, it would be a mistake to dismiss such an arsenal as ineffective. Necessity imposes discipline of its own. Systems that fail catastrophically are modified or abandoned. Configurations that work, even imperfectly, are retained and replicated as closely as possible. Over time, a form of functional selection occurs, favoring designs that tolerate inconsistency and operate within narrow but acceptable margins. Strategically, this produces ambiguity. External observers struggle to assess true reliability. Internally, planners accept uncertainty as a constant. This ambiguity can enhance deterrence by obscuring actual capability, even as it limits confidence in sustained performance. The arsenal's value lies not in durability, but in survivability under constraint. Ultimately, North Korea's war machine reflects the conditions of its creation. It is not an arsenal refined through abundance, but one assembled through persistence. Held together by necessity rather than cohesion, it functions unevenly yet deliberately, an expression of adaptation under pressure, where imperfection is not eliminated but endured.